Well, it's great to be back in person after probably 3.5 years or 3 years of intermittent and hybrid meetings, so it's wonderful to be back. I'm going to be talking about this notion of a simulated ground motion database today. And for those of you that were at the peer meeting last year, which I think was hybrid, just about a year ago, we talked about our plans for that particular development of simulated ground motion database without a lot of detail because we were just getting started. I'm back today to give you an update and talk about what we've accomplished and where we're going with this particular activity. So I want to acknowledge my co-PI, Dr. Floriana Petrona of the University of Nevada, and our graduate student, Parmita Ramani, and our postdoc, Majid Nia, that has been participating in this project as well at the get-go. And, most important, as Holland alluded to, this is really a deeply collaborative project. This is not something peer could do on its own, I don't think, without a strong collaboration with the national laboratories, because the data that we are using to feed the synthetic ground motion database is being computed on the world's fastest computers by a big team at the national laboratory. So as I get started, I would be remiss if I didn't give a shout out to that team that has been working on this DOE funded project for the last 6 years. And I'll talk about sort of the genesis of that, but these are folks that are seismologists and geophysicists. And because we're so heavily involved in high-performance computing, we can't do this without computer scientists and applied mathematicians as well. So this is a project that's led by Lawrence Berkeley National Laboratory in terms of the simulation, with strong contributions and collaboration with Lawrence Livermore National Laboratory. And you'll see as I go through, I'll explain a little bit about their role, Vice Peer's role. So I think you've probably all seen this figure on the left probably 50 times, right, at peer meetings. But it still does make a very important point. That is, we've become very adept, and a lot of great work has been done at utilizing motions from the past to try to understand motions for the future in terms of earthquake motions, to predict those motions. That is a self-limiting process at some level, in large part due to the sparsity of the data that's available. Look at the plot on the left. The vertical axis is the magnitude of the earthquake. The horizontal axis is the distance that particular ground motion data set was measured from the fault. What we see immediately, and this is the entire NGA database, the region we care most about, the yellow box, is the most sparsely populated region on that chart. And where is that? Big earthquakes in the near field. Very, very sparse data set. So it's natural that we would have a lot of uncertainty in our empirical models that are based on sparse data. In addition, as you see on the right, I'm going to talk a lot about the San Francisco Bay Area today because that's our first application. On the right, look at the last earthquakes we've had on the Hayward Fault, arguably the most dangerous fault in the country. Last earthquake was 1868, before anybody in this room was born. There was no such thing as a strong motion accelerometer. We didn't have those till the 30s. And so we don't have any data in the San Francisco Bay Area for a very, very large earthquake. So when we're doing simulation, that's a problem for us as well. We'd like to have data to validate our model. So I'm going to tell you how we are trying to build confidence in our computational models absent a really good data set to do traditional validation of our software. So as many of you probably know, the interest as well as the research efforts continue to grow in physics-based regional scale simulations. BSSA meeting this coming up in October that's being held in Canada is all about numerical simulation of ground motions. I would argue, and I think the role for peer, as engineers, as earthquake engineers, we ought to be just as engaged and concerned in this area as our seismological and geophysics colleagues are as well. We have just as much at stake in terms of the development. So what's the idea? Pick a region, giant region in the upper left-hand corner, create a computational model of that entire region to do simulations. And then, if you can convince yourself you've got a reasonable model, you can really play the what-if game, right? Take it to the computer. Computers can run a lot while we're asleep. They're cheap to run. And we can look at various scenarios and try to gain understanding, as well as add quantification, better quantification of some of the ground motions and infrastructure response. That's the idea. So PEER in 2021, to Holland's credit, decided to execute a Pacific Rim Forum, and that was, at the time, was entirely virtual because we're in the midst of the pandemic. And the purpose of that was to try to frame, take stock of where the technology is and try to frame a roadmap and a path forward. And I thought it was a great meeting. There were 261 international participants. One of the great things of a virtual meeting is you can have morning and afternoon sessions, and people from all over the world can come in, and 41 international speakers. And by the way, if you're interested, there's a very extensive report on the Peer website, and it's a report that has hyperlinks that you can click and go to the presentations and also see the slides. So there's a lot of information there. So during that meeting, and all these experts, ranging from researchers to practitioners, you know, we did the clicker thing, and we asked questions during that meeting, and we tried to get a consensus about what are the priorities for being able to move these types of developments forward and actually have them become practical. We don't want to admire this problem for the next 20 years. As practicing engineers, we want to move towards utilization and implementation. It's too easy to admire a problem. And so 3 things came out of that in terms of the voting. Number 1, what would empower the ability to move this technology area forward? Number 1, top answer, was the availability of an open access database that both researchers and practitioners could access. Check. Okay, we can do that. We're doing that. So that's one thing. Number 2, engineering design code guidance that is better for synthetic motions and more particular in terms of how you use those motions. We're not doing that in this project, but that's important. Number 3, development of rigorous acceptance criteria. How do you decide if these motions are reasonable before you start populating them out to the community, and the community comes back hostile and says, this can't possibly be correct, right? So those are 2 things that we're working on, the development of the database and the confidence building in the results of that database. 2 complementary projects on regional scale simulation are going concurrently. The first one is the LBNL and LNL development of the EQ-SIM simulation framework for high-performance computers. And this is a project that's been funded by the U.S. Department of Energy, and it's been going for about 6 years. It's going to concur and finish in December of this year. And I'm going to tell you what they're doing with that project that's so important to what we're doing for Peer. And then the second one, of course, is setting up the Peer database, and that's really the project I'll speak to in some detail today. These are computationally intensive problems. We can use every bit of computational power in terms of speed and memory that is available to us to try to solve this problem. What I'm showing you here is the evolution of the world's fastest scientific computer over time in that top chart. What do we see immediately? It's up and to the right, isn't it? It's always increasing remarkably over the decades. And so the latest rendition of that is being done by DOE, which has always been the pointy end of the spear in terms of simulation in this country. They are developing these GPU accelerated systems, not CPU, but GPU. Just think of that as another chip that's better at parallel processing information than a CPU. And the objective of the exascale computing project was to develop the world's first exaflop computer, the first computer in the world that could compute a billion floating point operations per second. If you want to do the math, if every person on Earth did a calculation once a second for the next 4 years, you'd have the amount of calculations that can be done by these computers in 1 second, just to put some context to that. So I'm happy to report that the world's first exaflop computer just was certified by the top 500 organization and came online in June 2023, just recently. And the whole purpose of the EQ-SIM development was to be able to work on those computers. I'm going to be accelerating here because I've got a lot more slides. So what is the EQ-SIM framework? It stands for Earthquake Simulation. And when they started the exascale program, the DOE requested proposals competitively for specific simulation projects that could be absolutely necessary to use this type of computational power and take full use of it. Our proposal was to model all the way from the earthquake fault rupture, propagate those waves through the earth, and have those waves appropriately interact with the structure when they arrive. It's a complex process. And so that's really what, in the EQ-SIM project, we've been doing. The top is the cartoon of that. The bottom is just an illustration of the workflow. We have to simulate the earthquake ground motions. We have to couple our ground motions to the structure appropriately, and then we can get some sort of risk map of the structure. So what have we been doing? Very briefly, we are utilizing the SW4 geophysics code, originally developed at Lawrence Livermore National Laboratory, fourth order in space and time, very refined code, summation by parts code. We've done a lot of implementations to improve the physics in that code in terms of the rupture model, to improve the algorithms in that code in terms of speed, to speed up the I/O, and then some very empowering algorithms that we've included, and I don't have time to go into it in great detail, but in particular, the manner in which we discretize the Earth. We've vastly improved that so we can really reduce the size of our models. So that's at the core of our simulations. This project has a heavy engineering emphasis on it, and so not just geophysics. So we have put a lot of effort into coupling our structural models with our geophysics model. And so we have a couple of options there. On the left-hand side, we can just do a simple weak coupling. We can take the ground motions and ground rotations, if we like, and impart those to the base of the structure. But we've also implemented the DRM, domain reduction method, developed by BLAC, so that we can appropriately honor the complexity of those incident seismic waves. The geophysics code is telling us the real wave field. It's not telling us a one-dimensional idealization of vertically propagating waves. It's telling us what the real wave field is. And so we can take that real wave field and interact that with our structure. We use this to study SSI, to do inclined waves, understand inclined waves and surface waves, and also some nonlinear soft near soil effects. And I raise this because this capability needs to affect how we do our database. This effort has been 6 years in the making. Won't go into a detail. A lot of this is developing the appropriate end-to-end workflow that is efficient. Anything you do when you're calculating these grids at 300 billion zones that's inefficient immediately exposes itself. So the ability to have computer scientists and applied mathematicians that can tweak and adjust these algorithms to operate seamlessly is very important. But we now can do the geophysics model, get our ground motions, save that database in a very special way, and then come back later and do our structural evaluation. So it's a multi-step process. EQSIM has made great strides over the last 6 years. This is just a plot. There's something, you don't need to get wrapped around the axle on this, but there's something called the figure of merit that we had to develop for this code to demonstrate our progress to DOE, and that is a measure of the performance of the code. What I'm showing you here are the advancements over the 6 years of this project and our ability to resolve and get better resolution of the ground motion simulation piece. We started, and we had a canonical model of the San Francisco Bay Area. We generated that as part of our project. It's the black box there, the entire region. We started at 3 hertz, just about 3 hertz, and a V sub S min, our minimum shear wave velocity resolved of about 500 meters per second. Over the course of this project and all those developments I mentioned, we can now run this problem, if we want to, at 15 hertz and 140 meters per second. The computational effort varies as the 4th power of the frequency resolved over the 4th power of the V sub S resolved. So climbing this curve is really, really hard, and we've made significant progress there. Another way of looking at this is comparing the EQSIM results with all previous results in the San Francisco Bay Area. I'll just say that all the color dots, the rainbow dots on the bottom were prior simulations, and you can see EQSIM, the blue dots, in what we've achieved over the life of the project. You see that increase in the gradient, and that is really a tribute to these GPU accelerated systems and the speed and the memory size of these. So what are we doing for the database? We are in the process of creating 20 different realizations of a magnitude 7 Hayward fault rupture. And I'm just showing you 2, and I'm showing you 2 bookends. These are the simulations. These are 390 billion grid point models, and we're resolving about 10 hertz here. And you can see a southern hypocenter rupture and a northern hypocenter rupture. Concurrently, we're taking in open seas a very detailed model, nonlinear model of a 12-story reinforced concrete frame, and we're analyzing at every single one of those points. So what do we see? We see the way the fault rupture has great impact on the damage distribution. It's not surprising. It's very clear when you run these 3D simulations, you immediately can see this effect of fault directivity. And so this is 2 bookend calculations, but we're going to have a whole bunch of these that we're going through now. We've run most of them. We're done with 17. We've got 3 more to go, but we will roll into this database. These are rich and interesting things to use. I'm showing you an example here of a northern hypocenter Hayward fault rupture. Now, a 20-story steel moment frame, the response at location A, B, and C, each of which are a kilometer off the fault. Identical earthquake, identical magnitude earthquake. Each one of these building locations is exactly 1 kilometer off the fault. But what do we see? I'm showing you as this winds down the dramatic difference in demand on those buildings as a result of the directivity effect. And so these are the kind of things we can play with and quantify. The building at point A, very near the hypocenter, has some moderate damage up in the top of the building. The building at point C, same building, has tremendous damage, both in the bottom and the top of that building. If you look at that carefully, you'll see that there's a factor of 4 difference in the demands on those buildings. And this is the kind of information we should know about, we'd like to have. If you look at the time histories on the bottom, you can see when you get down to point C, due to the stacking up of the waves, due to directivity, the fault normal component has a very large transverse pulse, and that's what's causing the damage in point C. We're working on the acceptance criteria, and Dr. Petrona is on point here. We are doing 2 things. At Berkeley Lab, we're doing a stress test. Talk about the banks and the stress test. We're doing a stress test of EQ Sim. We don't have big earthquake data, but we have 7 small earthquake data sets. So we are doing true code validation by modeling those 7 events, and each one of those events has about 100 sensor stations. And so we can compare our simulation results with those sensor stations. Secondly, for future large events, since we don't have any, we have to become a little more innovative. We're comparing those results with ground motion prediction equations to see if they look reasonable. And we're also getting self-similar data sets, historical data sets of ground motions, actual time histories, and comparing our simulated ground motion with other earthquakes that are very similar in terms of the velocity structure, the rupture type, and the magnitude of the earthquake. Very promising results looking at the Hayward Fault small events. And we had an epiphany, and our results had a bias until we became more sophisticated in how we calculated the corner frequency on this double couple source function. Once we fixed that, voila, I'm showing you here the residuals between which is the Fourier amplitude spectra of the simulations, vice the Fourier amplitude simulation spectra of the measurements, and you see there's not a lot of bias there. They're kind of not biased, which is really an important thing. On the right, you see some of the time history comparisons of simulation versus measurement. This is one site that they selected, and you see all 7 events at that site. The black stuff is the measured earthquake data, and the red and gold are the simulated earthquake data. So we feel pretty darn good about that at this time. So practically, and this came out of our discussions, I think, just about a year ago, people were saying, great, this simulated ground motion database is great, but don't mess up all the macro tools I've set up to pull down data from the peer database. So we're trying to honor, as we move forward, we're trying to honor the existing NGA database and try to make the simulated ground motion database look very similar to that so that it's easy for the researcher and the practitioner to access. Big bifurcation. The good thing is, with simulation, we can get very, very dense ground motions. A 10 hertz simulation with 140 meter per second resolution of the near surface soft sediment gives us about 1.1 or 1.3 billion sites in the San Francisco Bay Area. That's kind of overkill. We don't need that unless we're doing an SSI calculation. But the point is, that's good, but it's also bad because this creates a tremendously large data set. This example on log space, I'm showing you the data requirements in the vertical axis versus the number of ground motion sites. If we wanted to save all of that data for 10 realizations of the Hayward Fault rupture, it would take, at 10 hertz and 140 meters per second, it would take 3.22 petabytes. That's a problem. So we're going to bifurcate this problem. We're going to save those big data sets at the National Lab where they have gargantuan storage, and we're going to downsample for the peer database to a spacing that's not 1.7 meters. So for example, if you look very carefully, you see the current peer NGA database there. It's the golden. It's about 94 gigabytes. We can match that by going to a spacing of about a half a kilometer to a kilometer in this data set downsampling. So that's what we intend to do. So there's something for everyone in this, in my view, if we do this correctly. This is sort of the options that we see eventually in this database. We are generating surface motions right now with a linear model, and that's on the top. That's going to be the first set. We're going to move to having a near surface volume of motion so we can do soil structure interaction. But for those of you geotechnical engineers that are completely wedded to 1D site response calculations to do your nonlinear analysis, we can readily give you either in-column motions at the interface between the geotechnical layer and the rock layer, or we can scrape off the geotechnical layer and give you rock outcrop motions. And so these are options. We'd like you to come to our next workshop to discuss these options and pitch your interest. We need to be able to scale this data set. We talked about 20 realizations of the Hayward Fault. With Frontier, we're now running simulations of the San Andreas Fault in magnitude 7.5 earthquakes on the right. And if you live in Santa Rosa or Livermore, look away from this, because what you're going to see is those waves emanating and radiating from the Hayward Fault get trapped in those basins and rattle on forever. So if you look at it on the right, it's not surprising that Santa Rosa was completely clobbered in the 1906 earthquake. There's a 20-mile long basin there, as well as in Livermore, a deep basin where I live. And these waves, you can just see, you're starting to see the resonance in the Livermore basin now. I'm over time looking ahead. As Halda mentioned, DOE has agreed to support some of this effort. They're going to support a workshop, a peer LBNL simulation workshop. We may target January or a little later. We're still working those details out, but I make that in red, and I hope you'll all be interested in that. We're completing the assessment of the full suite of the 20 realizations. We're getting close. We meet every week, we argue about these things, and we look at these critically. We want to put something out that is reasonable and defensible so we don't get this backlash of these look like crap. We just don't want to do that. We're going to build out a new data server at Peer that's dedicated to these simulated motions. DOE has just given Peer money, significant money, to develop that hardware and for the IT support. And then, of course, we'd like to select a set of early users that we can work with to test this system. And so we're looking for people to raise their hands as we move forward. And I am well over time, so I'm going to stop there.